47 says, approximately how much less than 4 is the cube root of 63? And so we're talking about the cube root of x as a function, right? F of x is our function. And using a tangent line approximation, or using linearization here, we should be able to approximate the value of the cube root of 63 using L of 63. And L of 63 should be equal to F of 64 plus F prime of 64 times 63 minus 64. That's your linearization. F of A, and remember A is the value that you can evaluate f of x at easily. So f of 64 plus f prime of 64 times 63 minus 64. This is the actual approximation for the cube root of 63. And so f of 64 is 4. F prime, if f is cube root of x, that should be 1/3 x to the negative 2/3. And so we'll end up with 1/3 of 64 to the negative 2/3, which we'll evaluate in a second, times -1. And this gives us 4, and then 64 to the negative 2/3, that drops to 64 to the 2/3 in the denominator. The cube root of 64 is 4, squared is 16, so we got 4 minus from the -1, 3 times 16, 148. And so we know that the value for the cube root of 63 is 1/48 of a unit less than 4, which is what it asks. How much less than 4 is the cube root of 63? Good on 47, everybody? Any questions there on that one? All right. 65. Okay, I think I just did this one last period. 65 says 2 tangents can be drawn from the point 3,5 to the parabola y equals x squared. And we want to find their slopes. So this one's a little complicated. But we could write the equation of the tangent line, the generic equation of the tangent line, as y minus 5 equals the slope times x minus 3. And what would the slope be? Well, the slope would be the derivative. It would be 2x. So we should be able to say that y minus 5 equals 2x times x minus 3. And that's the equation that we need to solve to figure out what x values these tangent lines fit the curve. And so in order to do that, we can just take y equals x squared, plug that in for our y, and get x squared minus 5 equals 2x squared minus 6x, and then solve for x. Subtract the x squared gives us x squared minus 6x and plus 5 equals 0. X minus 1, x minus 5, which gives us x equals 1 and x equals 5. But those are not our answers, even though those are an answer choice, because our slope is 2x, so we got to plug those in to get slopes of 2 and 10. So the slopes of those are 2 and 10. Does that make sense to everybody?
Wait, so is this question asking for like the slope of the tangent line that like also intersects 3, 5?
Correct. Yep. It's saying there are 2 tangent lines to this parabola that happen to go through 3, 5. Not that those tangent lines are tangent to the parabola at 3, 5. But they happen to go through the point 3,5, right? Because I mean 3,5 is not on this parabola, so they can't be tangent to the parabola at 3,5. Does that make sense? Or no? Right, I've got a parabola, and I've got the point 3,5, and somewhere along here there's a tangent, and there's another tangent that, you know, I didn't extend my parabola out far enough to show the other one, but somewhere out there there's another tangent line to that parabola that goes through 3,5. Okay. Next one on my list is 83. So looking at 83, it says for question 82, if t is the number of hours of travel afternoon, then the cars are closest together when t is something. So problem 82 says we got two cars on a perpendicular road. Car A is going at 40 miles an hour. Car B is going at 60 miles an hour. At noon, car A reaches the intersection. Let's say A is traveling this direction. And then car B is 90 miles away moving toward the intersection. So we'll say that's up here, moving this direction. And we wanted, so in 82, we wanted to know when is the distance, or what rate is the distance between the cars changing. So that'd be, you know, we draw a right triangle there, and we use a related rate to find that. But this is a little different. It says if t is the number of hours of travel afternoon, the cars are closest together when t is. So the closest together would be when this hypotenuse is the smallest. So let's call this y, let's call this x, and let's call this z to start with. And we want to minimize z, which should occur at the same value as a minimum of z squared, which will be helpful to us if we use x squared plus y squared equals z squared. We should be able to minimize z squared and find the x value at which that happens, rather than necessarily having to take the square root and do it that way. And then we should be able to write both x and y in terms of t with any luck. So what is x equal to? If t is the number of hours after noon, it's moving at 40 miles an hour. So x should be 40t. And y started out 90 miles away, but is decreasing by 60. So that y should be 90 minus 60t. So that should be our z squared value. And so then we just need to take our derivative here and solve for t. So the derivative with respect to t of all of this, 40t squared is 1600 t squared, so that'll be 3200 t when we take the derivative. And then this one, if we were to distribute that out, that's going to be 90 times 90, which its derivative will be 0. And then we're going to have negative 5400 t and another negative 5400 t. So that'll be a negative 10,800 t. And when we take the derivative, we'll lose the t on it. And then this will become a plus 3600 t squared, which will make a plus 7200 t. And if we set that equal to 0, what do we end up with? What does that come out to be?
27 or 26.
Good to me. Choice B. Does that make sense to everybody for 83?
Do you have to do a sign chart or no, since it's the
Oh,
only
yeah, sorry, we should do a sign chart, yeah. So 27, 26, plug in something like 1 to your derivative. If I plug in 1, I get a negative value. And if I plug in something more than 27, 26, like a little bit more than that, like 2, I should get a positive value. So, yeah, comes out to be a minimum, but yeah, you should. Any other questions there on 83? All right, the next one I had on my list was 34. So 34 says the area of the largest rectangle that can be drawn with one side along the x-axis and 2 vertices on the curve of y equals e to the negative x squared. So we need to figure out that. What does y equals e to the negative x squared look like? Nobody? Looks sort of like this. It's symmetric across the y-axis, so we're talking about vertices like this. So it's going to look something like that. 2 vertices on the x-axis, 2 vertices on y equals e to the negative x squared. And so the length here should be 2x, because this is x, and if this is symmetric across the y-axis, each of those should both be x. And then our height should just be e to the negative x squared. So our area formula should be 2x e to the negative x squared. And we want to know the largest, so we want to maximize this area, so we need to take its derivative. So 2x times the derivative of e to the negative x squared, which is e to the negative x squared times the derivative of negative x squared, and then plus the derivative of 2x, 2 times e to the negative x squared. Everybody good with that setup so far?
Yes.
We'll factor out the 2e to the negative x squared, leaving us with a negative 2x squared plus 1. And we need to figure out when that's equal to 0 and when it's undefined. It's never undefined, but it should be equal to 0 when either of those is 0. The first part's never going to be 0, but negative 2x squared plus 1 could be 0. Should be x squared equals 1/2, or x equals plus or minus root 1/2, which the negative doesn't make any sense, so we'll just call it the square root of 1/2. And looks, what does it say? It says the actual area, so then we got to go plug in the square root of 1/2, and we should check to show that that's a maximum. So square root of 1/2, plug in something less than that. Let's say like 0, we get a positive and a positive. Plug in something more than that, like 1, we get a positive and a negative. So it's clearly a max, and we'll just plug in square root of 1/2. 2 times the square root of 1/2, which I'm just going to start writing it as 1 over root 2. And then e to the negative and the square root of 1/2 squared is 1/2. So we have a root e also in the denominator, so 2 over root 2e, which of course doesn't look like any of our answer choices, so we'll have to rewrite that. So we should be able to note that 2 is root 2 times root 2, and this is root 2 times root e. Cancel those out, and you get root 2 over e, which is answer choice A. Good or no on 34?
Good.
Wonderful. All right. Next one I got on my list is 35. I remember doing 35, but I don't know if it was in this class. We got a line that goes through the point 1, 2, forming a right triangle with the positive x-axis. Did we do this one?
Yeah.
We did? Okay. I couldn't remember if it was this class or the other. Okay. All right, so we don't need to worry about 35. Next one on my list was 37, which I know we did because we just talked about that a little bit ago. Did we do 49?
We did 49.
We did 49. Okay, we're good there. Next one I got on my list is 8.
We did 8.
We did 8. All right, next one I have on my list is 15. I don't remember doing this one in any class period, so we must not have done 15. 15 says the total number of local maximum and minimum points of the function whose derivative is given. So our derivative is x minus 3 squared, x plus 1 to the 4th. We want to know the number of max or min points on that one. And so one thing that, I mean, we should be able to, first off, just really easily go in and make a sign chart with our values. So like x equals 0 makes this 0, x equals 3 makes this 0, and x equals -1 makes this 0. So you go in and make yourself a sign chart if you want, plugging in each of these values, and you'll see that there's just one of these makes a minimum. I'll explain why in a second. So plug in like -2, you get a negative times a positive times a positive. In fact, these terms, x minus 3 squared and x plus 1 to the 4th, are going to be positive no matter what, aren't they? No matter what x value I plug in. So really, all I need to look at for my sign chart is just this x, because all the rest of this junk is positive. So plug in -2, I get a negative, decreasing. Plug in something still negative, still decreasing. Plug in something positive, it starts increasing. Plug in something else positive, continues increasing. So we just have the one value, which tells us that it's choice B. But if you have a critical value and that critical value has a multiplicity, right, squared or to the 4th, right, even multiplicities are not maxes or mins on the roots. Odd multiplicities on your roots, or sorry, your critical values, will be a max or a min. So we would have known for sure there's only 3 critical values, and we would have been guaranteed that these two did not create maxes or mins, only that one could. Everybody good there with 15?
Yes.
Cool. All right, next one on the list that I've got is 34, which we just did a minute ago. 36, which we've done, 37, which we've done, 39, which we've done, 47 and 49, which we've done. All right, we're looking good there. Next to the next person, 7. I did 7. I did 7 in the other class period. I don't actually remember doing it. We have y squared minus xy plus 9 equals 0. And we're trying to figure out when the tangent is vertical. Did we do that one?
We didn't.
We did not? Okay. All right, so we want to know when is the tangent line, that's not an L, tangent line vertical. So tangent line will be vertical if the derivative is undefined. So all we need to do is take the derivative of this and see when it's undefined. So since this is not an explicitly defined function y as a function of x, we have to do it implicitly. So 2y dy dx minus, and then xy is a product of two functions. So we'll do minus x times derivative of y, and then we'll do derivative of negative x minus 1 times y, plus 9 becomes 0, and equals 0 is still equal to 0. Everybody good with the derivative there to start with? We'll factor out the dy dx on the left side there and add the y to the other side to give us dy dx equals y over 2y minus x. And in order for this to be undefined, the denominator needs to equal 0. So that would tell us that x is equal to 2y. So in order to figure out when that's true, we'll take every x in my original equation and replace it with a 2y. And solve for y. So y squared minus 2y squared is negative y squared. Subtract the 9. What negative y squared is negative 9 tells us y squared is 9, or y is positive or negative 3, which appears to be answer choice D. Good or no? Any issues with 7 there? Okay, and then we did 8. Somebody already said, right? We did 8, and then next on my list was 10. I remember doing 10, but I don't remember if it was in this class period. Did we already do 10?
We didn't.
We did not. Okay, cool. So number 10 says the side, and we're calling the side E for some reason, I guess for edge maybe. The side of a square is increased by 1%. Okay, so E is increasing by 1%. And we want to know how much the area will increase approximately. Well, the area is E squared. If E increases by 1%, that tells us that the change in E, dE, is 1% of E. Well, what is 1% of E? That's 0.01 E. Right? And so if dE is 0.01 E, we can say dA is 2E times 0.01 E, or E is just some, I don't know why they're using E as the variable, but that's fine. So that would give us 0.02 E squared. Looks like choice B. Does that make sense? So it's just a differential equation, but they did it in terms of a percentage of the amount, of the original amount, rather than two numeric values. Is that good for number 10?
Yes.
All right. That is all of the questions that people asked for yesterday. So I know a couple people asked about stuff today. So the first one was actually doing 33, so we'll do that real quick. And gosh, I'm still flabbergasted with myself for changing that without really looking over that repeatedly. A local minimum value of the function y equals e to the x over x is, and it should be e, answer choice D, which is e. But we'll take our derivative to find when we have a min or a max. So y prime should be denominator times derivative of numerator minus numerator times derivative of denominator, all over denominator squared. That's just our quotient rule. And we want to know, when does this equal 0 and when is this undefined? Well, it's undefined if x equals 0 which we can ignore because x equals 0 doesn't exist in our original function. So then we'll just set x e to the x minus e to the x equal to 0, factoring out e to the x, giving us x equals 1 as the only potential place. So plug in 1, make sure it's a minimum. So we plug in 0 to our, well, we can't plug in 0 to our derivative. If we plug in something between 0 and 1, like a half to our derivative, our denominator is positive, but our numerator ends up being negative, so we're decreasing. And if we plug in something more than 1, like 1,000, we have a positive number over a positive number. So it's clearly a minimum at 1. And then to find out the actual minimum value, we look for y of 1, which is e to the first over 1, or e. That makes sense to everybody for 33?
Mm-hmm.
Sorry, did somebody say something? I couldn't understand that if you did.
Oh, I just like said, yeah, that's good.
Oh, wonderful. All right. So next one I've got on my list. Sorry, hold on one second. Okay, sorry about that. So next one I have on my list is 50. So 50 gives us a graph that looks like this, calls this f of x. And it says this is called cx squared plus dx plus e. And we want to know about c, d, and e being positive or negative, effectively. So first off, what's your y-intercept? Your y-intercept of this function is when x is 0, so your y-intercept should be e, right? Which tells us that e must be positive based on the graph. So that should eliminate, I'll write out A, B, C, D, E. If E has to be positive, that eliminates choice B. Next thing is this function is decreasing. So let's take a look at f prime. The derivative is 2cx plus d. Okay, and so if we look at, let's say at x equals 0, the derivative should be negative because this function is decreasing. The slope is negative of the function there. And so at x equals 0, that'd be d. So d must be less than 0 because f prime is less than 0 at x equals 0. So d has to be less than 0, which eliminates choice A. And it eliminates choice D, leaving us with just C or E. And then we'll take a look at the second derivative. F double prime should be 2c. And 2c needs to be greater than 0. Not greater than 0, needs to be less than 0 because this is concave down, which tells us that c is less than 0. And so the only one left is choice E, where c is less than 0, d is less than 0, but e is greater than 0. Good on 50 there?
Could you just say that C is negative because you know it's a parabola and it's opening downward, so the A must be negative?
Yeah, that'd be fine too. Sure. Yep. All right, next one, I got a couple more here. 54. So 54 gives us a graph that looks like this, and it's called f prime. It looks like this happens at 4, and this is 5. I guess I didn't make that quite as steep as I should have, but that's fine. And 54 says from the graph, it follows that f is discontinuous at x equals 4, f is decreasing for 4 to 7, et cetera, a bunch of different things. Okay, so let's just sort of take each of these step by step and see which ones we can eliminate. So choice A, f is discontinuous at 4. Well, for something to be discontinuous at a point, if it's discontinuous there, its derivative would have to not exist at that point, and our derivative exists at all of the values here, all the way up to 7, which is where it ends. Okay, so our derivative exists everywhere, which means our function definitely exists everywhere, which means that it's going to be continuous. I mean, it doesn't guarantee that it's discontinuous. It's possible that it could be, but it doesn't guarantee that it is. So we can eliminate choice A. Choice B says f is decreasing for 4 to 7. So if f is decreasing, that means f prime would be negative from 4 to 7. Well, f prime is not negative from 4 to 7. F prime is positive from 4 to 5, and then negative from 5 to 7. So that doesn't make any sense. C says f is constant for 0 to 4. Well, that's also not true, right? The slope is constant, right? Which means that it's, suppose that number is like 2 or 3, it means that the function is increasing at a constant rate. The function looks like this from 0 to 4. So it's not constant. For the function to be constant from 0 to 4, the derivative would have to be 0 from 0 to 4. Because then the slope of the function would be 0 and you have a horizontal line. Let's see, and then choice D says f of 5 is less than f of 0. So f of 5 and f of 0, right, the 0 value, the slope is positive. So my function is increasing fairly rapidly from 0 to 4. And then from 4 to 5, my function is still increasing, but just less rapidly, right? It has a still has a positive slope, and it's increasing but less rapidly from 4 to 5. And so the value at 0 is actually going to be far less than the value at 5. So choice D doesn't make sense. And then choice E, f of 2 to f of 3, f of 2 is less than f of 3. That makes sense because my function is increasing from 0 to 4 at a constant rate. So at 2 and at 3, I should still be increasing past 2 to get to the value at 3. Looks like that one should be choice E. Everybody feel okay about that with 54?
Yep.
All right. And the last one that I have on any list here that people have asked for should be number 60. And so number 60 says, how many times, we need to go back and look. We've got another graph here for number 60 that looks like, it's supposed to be flat there, flat from 0 to 1, down from 1 to 2, down again from 2 to 3, but a little steeper, and then 3 to 5. This is 5. This is 3. No, that was not 3. This is 3. This is 2. This is 1. This is negative 10, and this is 5. Okay, all right, that's what our graph looks like. And this is the velocity time graph. Okay, and so it then says for 60, how many times between 0 and 5 is the object's acceleration undefined? And so the acceleration should be undefined whenever whenever we can't find the derivative of the velocity function. So acceleration is undefined if you can't differentiate velocity. And so since this is the velocity graph, the derivative of the velocity graph should be undefined at any corners or cusps or vertical tangents or discontinuities. But we don't have any we don't have any cusps, vertical tangents, or discontinuities. But we have a corner at 1, we have a corner at 2, and we have a corner at 3. So it looks like it should be undefined at 3 different times. So choice, what is that? Choice D, it looks like. Good or no?
Good.
All right. Anybody else have any questions there? All right. That is it then on multiple choice applications of the derivative, which leaves us with just enough time to do one differential equation free response question before we're done for today. So we will start with this one, the first one that we're going to do. A couple things to note before I have you start working on this. Number one, the part where it asks you, which in this one is part C, for you to find the particular solution to it. Pretty much every time you have a differential equation free response question, one of the parts will ask you to find the particular solution given an initial condition. That part is usually weighted to be at least 5 out of the 9 points. And the other 2 parts should be pretty quick and easy. In fact, most of them should be fairly quick and easy for all of these differential equation ones that involve slope fields. But the majority of the points will come from finding the particular solution given the initial condition. Okay? So if you have to focus your time on something, maybe focus on that one. If you're short on time, knowing that can give you the most points. Other than that, I'll let you guys read through it. Not all of the parts require integrals, really only the part where you have to find the particular solution does. So I'll give you guys 15 minutes to work through this, and then we'll have just enough time to get through it before class is over. And this is up in the blank notes as differential equation FRQs, if you want to get your own copy of it to write on something. All right, so 15 minutes starts right now. Ready to go. So the first part A, just ask us to sketch the solution curve that goes through 0, 2 and through 1, 0. So the solution curve through 0, 2 is pretty straightforward. It's just that horizontal line. Right? And the solution curve through 1, 0 looks about like this, something like that. And those should have been a pretty straightforward, easy 2 points. Just follow the slopes, 1 point for one and 1 point for the other one. It states in the scoring guidelines that you need to follow the trajectory, you need to go through the actual points, and you need to extend to the ends of the boundaries of the slope field. Okay, so that's how you would have made sure you got both those points. For part B, B was the one where it asked you to find the particular solution, or not to find the particular solution, but it says f of x is the particular solution through the point 1, 0. We want to write an equation for the tangent line to f of x at x equals 1. So if f of x is the solution to this, then that means that this is the derivative to y equals f of x. So we can use that derivative at the point that they tell us about, 1, 0, to find the slope of f of x. And so we'll just plug in 1, 0 into here. 1/3 of 1 times 0 minus 2 squared gives us 4/3. So we have a slope of 4/3. And the point is the point 1, 0. So in point slope form, y minus 0 equals 4/3 times x minus 1. And getting the slope here was 1 point, and getting the equation was a second point. Everybody good there? All right. So for part C, it then wants us to actually solve the differential equation. So we need to go back and we need to write out dy dx equals 1/3 of x times, what was it, y minus 2 squared, I believe. Yeah. And so we need to solve that differential equation with the initial condition that f of 1 is equal to 0. Oh, yeah, sorry. That's right. We were supposed to approximate this at 0.7 for part B. And that wasn't a point. This was 1 point, and the approximation was another point. So y equals 4/3 times 0.7 minus 1. And so what does that come out to be? That's negative 3/10 there. So that should be y equals negative 2/5 if you simplify that out. So that was the other point. Sorry, I forgot to do that last little part there. Thank you, Kylie, for mentioning that. All right, everybody good with part B now?
Yes.
Okay. All right, so part C said to solve this differential equation with the initial condition. And so this is a separable differential equation. And anytime you have the separable differential equations, the first point is always given to you if you just separate the variables. So dy over y minus 2 squared equals dx, I'm sorry, 1/3 x dx. So this right here was 1 point. Then you got a second point if you integrated the left side correctly. So this is just u to the negative 2, so negative 1 over u, since du is the same as dy in this one. So that was another point, second point there. And then integrating 1/3 x to give you x squared over 6 is a third point. And then don't forget to put your plus c. If you don't put the plus c, you can't get more than 3 points on this. But to get the separation in each integral is 3 out of the 5 points that part C is worth. So then to get the fourth point, you have to actually plug in 1 for x and 0 for y and find your constant. So if y is 0, that gives me a half over here on the left, and x is 1 gives me a 1/6, and my constant then becomes a half minus a 1/6, or 1/3. So that's your fourth point, was putting in the c and then using your initial condition to solve for the constant. And then your fifth point is finishing solving for y. So x squared over 6 plus 1/3. And we would get ourselves a common denominator if we wanted to take the reciprocal, or we could just write it as negative y minus 2 equals 1 over this, if you want. Personally, I prefer to write it as this, and write it then as 6 over x squared plus 2. So that's how I'm going to finish it off. But if you do this, you can then divide by the negative and add the 2, and that's acceptable. I think it's better to do it this way. So I divide by the negative 1, gives us negative 6 over x squared plus 2. And then I'm going to add the 2 to make it 2 minus that is what y is equal to. And It doesn't specify that you need to state an interval of validity, so you don't need to. In the scoring guide, it puts a note for what the interval is, but this is good enough. And that's your 5th point. Any questions on that one? We're going to do a bunch more like that in the next few days, just to practice them. All right, so that's where we'll end.